So in this video then, I am going to be running through some Hess's Law questions. Now, I'm not going to be focusing on straightforward Hess's Law questions where you simply put the arrows in and you get your answer out fairly quickly. I'm going to be focusing on some more difficult, more challenging Hess's Law questions that require you to almost think outside the box in terms of how you approach the question. So I'm going to start by looking at this. It looks very, very complicated at first glance, okay? It is aluminium and aluminium chlorate. It's a very unfamiliar reaction, but they give it you in full. But notice they're giving you the delta H already. The delta H is here. Okay, so we'll get onto that in a minute. Okay, so quick little start then. 3 marker. This is straightforward. Entropy of formation. I'll just quickly run through it. I don't think it's particularly important, but essentially entropy of formation, 1 mole of a compound, that's the first mark, and it is produced from constituent elements, that's the second mark, produced from constituent elements under standard conditions, and then it says give the standard conditions for the third mark. So that's what, 298 Kelvin, 1 atmosphere pressure. That's all you need. You can also put 1 mole dm cubed if you want to solutions, but it's not really important. The temperature and the pressure is the main one. So equation including state symbols for the reaction that represents the standard entropy of formation of NH4ClO4. So again, based on the definition we've just wrote, okay, I'm going to make 1 mole of NH4ClO4 solid, include the state symbols, and I'm going to make it from nitrogen, N2, which is a gas. I'm going to make it from H2, which is also a gas. O2, well, the gas, all the gases, and then chlorine, which is also a gas. They're all diatomic as well. And then just balance it. So I need a half Cl2, I need 2 O2, I need 2 of those and a half of those. There you go, straightforward. Okay, again, you have to use halves because I have to make 1 mole of my final amount. I can't make 2 moles of it because that's not the standard entropy of formation. Right, that out of the way. This one, calculate the entropy of formation of NO, nitrogen oxide. So let's go back to my equation. They've given me delta H. I've got to work out what this is. And they've given me the values for all the others. So this is where it gets complicated. Because all of a sudden, I've already got one of my, I've got to work backwards now, essentially. So it's important now this is where understanding Hess's law and what it represents conceptually is far more important, because a lot of students just memorize how to work out regular Hess law calculations by just doing reactants minus products or products minus reactants, which is great and it'll get you the marks most of the time. But if you don't have a conceptual idea of what's going on here, you're going to struggle to access this question. So let's go down and let's see what we can make of this. So I'm going to do it up here and I'm going to make it look a bit messy because I don't want to keep scrolling up and down to get to the numbers. But in reality, I'm given entropy changes of formation in my table. So we know, hopefully, from what regular Hess's law is, that the arrows are going to go up. Okay, and the bits at the bottom are just going to be your elements in their standard states. I'm not going to write those down. Okay, I'm just going to write elements. Okay, these are the elements that would be there. Because I'm really just interested in what's on these lines. So I'm told that delta H for the top reaction is minus 2677. I can now work out the rest of it, essentially. So I can work out everything on the arrow here on the left-hand side because I'm given, well, there is no value for aluminium because it's an element on its own, so there is no entropy of formation for an element. And I've got 3 lots of NH4ClO4, so I just have to do 3 times minus 295. And that gets me minus 885. Now, that means that this arrow is minus 885. Now, I've got to work out everything on this arrow apart from the bit I don't know. So let's just put it all in. So I've got aluminium oxide, so that's minus 1676. Add that to 6 waters, so 6 lots of H2O, so 6 times minus 242. And also I've missed aluminium chloride there as well in my haste. Add an aluminium chloride on plus minus 704. And that gives me a grand total of minus 3832 plus my unknown. Now my unknown is 3 lots of NO, which is just, I'll put 3x. Now from here, we just have to figure out how this all links together. So, based on Hess's law then, the route taken by a reaction is independent of the path taken. So, you can't just do this a normal way. You have to think about how they link. So, I'm going to just change colour. If we start from the constituent elements, okay, I'm going to start here, and we want to get to the products of the reaction, there are 2 ways we can do it. We can either just go literally straight there, as in the first route, or we can go this way. We can go up here and around the other side, like that. And that's route 2. And Hess's law tells us that route 1 is equal to route 2. Both will give us the same answer. That's a really useful equality, because that means that route 1, which is minus 3832 plus 3x, is equal to minus 885 plus 2677. And we can simplify that even further, because minus 885 plus 2677, well, sorry, plus minus 2677, my bad, I've missed a negative sign there. Let's be careful of that, it's easily done. Gives us minus 3562. So nice and straightforward now. It's a very, very, very straightforward rearrangement, in fact. So all we now need to do, let's just go down a bit. Okay, so if minus 3832 plus 3x equals minus 3562, then I can rearrange this very, very easily and just say that 3x equals minus 3562 plus 3832. So just add 3832 and I get 270. So 3x equal, oh dear, what have I done there? My pen's just gone a bit funny. So 3x equals 270, and therefore x equals 90, and that will be your answer, and it's a positive number, plus 90. And there you go. Nice and straightforward. So, I mean, I say straightforward. There's a lot of work to do here, so hopefully it's clear how I've done this. Okay, I've not used the standard, the standard way of computing Hess's law. What I've done is I've put in all the information I have and then just used an equality and found that, used Hess's law and applied it to this, rather different looking Hess cycle. Okay, going route 1 is the same as going route 2. Okay, getting from start to finish 2 different ways is the same energy. I've used that equality to form an equation which I can then easily simplify and rearrange to give me the answer I want. There are other ways to do this. Okay, so there's definitely other ways you can go about doing this. However, in terms of when you're looking for an unknown compound that isn't in the table, I think this is the easiest way to do it so that you don't make mistakes. If you're just doing a regular Hess cycle and you're looking for a delta H for a reaction, there are better ways to do it than this equality method, I think. But in terms of working out an unknown compound, this is where application of knowledge is far superior to just brute force memorization. So hopefully that made a bit of sense. It's one of the hardest Hess law questions I've come across on an AS paper. So I'm not sure, it might have been an A-level paper actually, but it was definitely one of the harder questions on on just this topic alone. So having said that, Here's another question that you might be asked. Okay, now they're giving you an unfamiliar enthalpy cycle, but luckily they've given it for you. Now, what I will say is they've given 3 reactions here that link by reaction of HCl. So you've got reaction 1, reaction 2, reaction 3, and they link following this cycle. Notice this isn't the standard combustion or formation cycle. It is, essentially different in its entirety, but don't let that throw you off because the arrows are still the same. It's lucky because they've drawn it for you. In some exams, they won't draw that for you, and you'll be expected to figure out how to construct it. Just to show you how to construct it, if we look at reaction 1, that's just along the top. You can take any reaction, like, so reaction 1, stick it along the top. Notice that the reactant in reactant 1 is also in reactant 2. And the product from reaction 1 is in reaction 3. And they're both adding the same thing. Bit like combustion. Combustion, you're just adding oxygen. This is adding HCl. And you end up with the same products as well. So this is how you can link them. They're taking the reaction, so the reactant and the product, added the same chemical to form a common link. Okay, that's commonly how you construct these cycles. From this, of course, then, they give a bunch of information. Okay, now, they're not going to tell you what reaction 1 is, but instead, they'll tell you what reaction 3 is. Reaction 3 is minus 136.1. And then you have to use the student's results to work out reaction 2. Now, this is a Q equals MC delta T question. So, I am going to quickly just run through this. I'm not going to spend much time on it because there's another video on it, but we'll just run through how to calculate it. So it's Q equals MC delta T. The mass is going to be the mass of the final solution. So in this table, we have the mass of the final solution and the polystyrene cup, and without, so we simply take the difference of 124, so take 124.425 minus 21.415, the weight of the polystyrene cup, and the mass, therefore, is 103.01. Have I done that right? Yes, I have. Okay, 0.01. Heat capacity is always 4.18. Delta T is this position, so it's 25.40 minus 20.40, so that's quite nice, it's just 5. Slap all that in the calculator, and you get the big number, so as you should. So I'm just going to do 2152.909 joules, which is then just 2.152909 kilojoules. You then have to work out the amount of moles. Now, interesting part here. Do you use the moles of MgCO3 or the moles of hydrochloric acid? Well, if you can see here, as I've said before in a different video, the hydrochloric acid is in excess, don't use it. Okay, you need to use the one that fully reacts. So MgCO3 is what you want to use. So the moles of MgCO3 is going to be mass over molar mass, 4.215 over the molar mass of the total. So magnesium is 24.3, carbon is 12, oxygen times 3 is 48, which gives me 84.3. And therefore 4.215 over that gives me a nice even number, which means you always know you're on the right line when you get a nice even number, 0.05. And then delta H is simply, for this reaction, 2. For Q over N, so 2.152909 over 0.05. Again, keep the numbers in the calculator. Don't be tempted to round yet. Okay, it's very, very tempting, but don't do it. Ignore it. Try your best, and you get 43.05818. Again, that's a negative number because it's an exothermic reaction. And now it's just a matter of plugging it in. Okay, because you're told that reaction 3 is minus 136.1. So this is minus 136.1. And my value is minus 43. 0.05818. And then you can just work out the reaction 1 very, very easily by just doing one plus the other. So again, this is a basic Hess's Law 1, so I'm just going to follow this arrow down. So I'm following the arrow down, so I keep the number the same, so minus 43.05818, and I'm going back up this arrow, so I'm doing the opposite of this number. So instead of minus 136.1, it's plus 136.1. So I do my answer plus 136.1, and I get 170. That can't be right. Hang on. Minus 43.05818 plus 136.1 is 93.04, and that's positive. Okay, and that's not a surprise because this is a thermal decomposition, so it probably should be endothermic. And that's it. That's the whole thing. Okay, and you need all these lines to answer it apparently, and I used this little bit here to do it. So again, straightforward. Again, it links things in together as well. So Q equals MC delta T links in quite nicely here. But once you've worked out the delta H, this is a very, very straightforward cycle, and you get your answer. But just be aware, they will give you sometimes some unfamiliar cycles to look at. But just because they look different doesn't mean they are particularly different, and you can still tackle them in the same way.